If we look at 7.4 from our textbook, we're going to solve equations using logs. Okay, so a lot of the questions that we're going to solve today, we're going to have to use okay, so we're going to use and apply our laws for logarithms. And so our laws of logarithms are that if we have something within a log that's raised to an exponent, we can pull that exponent down out front, and we'll say that's n times log a. Okay. If we have two things in our log that are multiplied together, say n times m, we can split those apart with addition. And similarly, if we have division, we can split those apart with subtraction. Okay. We'll keep in mind that log of any number with the same base is 1, and that log of 1 is 0. So we're going to be using kind of these 5 things, and in different orders, right? Sometimes it'll be helpful if we take our exponent and put it down front. Other times it'll be helpful if we take our exponent and put it back in. So there'll be a lot of problem solving, and there's no one way to solve them, so that's why we'll try and see as many examples as we can. So our first example, we have log x plus 1 plus log x plus 4 equals log 5. Okay. So looking at this, what rule do you think we could apply right off the bat? Which one of our laws of logs? So because we have addition over here, we have two logs that are added together, we could take this left side and say that's the same as log x plus 1 times x plus 4. So we're just pulling those together using our product law. And that equals log of 5. Okay. So now we're looking at this. We have an equation that's equal with one term on each side. Both of those terms are taking the logarithm of both sides. So if we have the log of something equals the log of something, we know whatever's inside of our logarithms has to be equal for those equations to be equal. So now we can say that x plus 1 times x plus 4 equals 5. Okay. And how can we solve that? We're going to have to expand out this left-hand side, so we'll get x squared plus 5x plus 4 equals 5. We can bring that 5 over to our left-hand side, so we'll get x squared plus 5x minus 1 equals 0. And now we're looking to solve this. Can we factor it? Can we find two numbers that multiply to -1 but add to +5? It doesn't look like it, so we're going to have to use the quadratic formula. We can say that x equals -5 plus or minus 5 squared minus 4 times 1 times -1 over 2 times 1. And with a little bit of work, we can get that x equals -5 plus or minus the root of 29 divided by 2. So from here, we're going to split that into two solutions. We have a solution that is x equals -5 plus root 29 over 2. And we have a solution x equals -5 minus root 29 over 2. So we go through and we can evaluate. We have x equals 0.1926. and we have x equals negative 5.19. Okay, so we have two solutions. We have to check our solutions though, because one of them may not be valid. So we go up to our original equation. And what do we know about logarithms? What do we know about the value that we're taking the logarithm of? It has to be positive, okay? So we know that whatever is inside our logarithm has to be positive. We need this to be greater than 0. So from our first one, we can get a restriction that x has to be greater than negative 1. From our second one, we get a restriction because this one also has to be positive. We get a restriction that x has to be greater than negative 4. So kind of the one that rules out the most is if we have x is greater than negative 1. Okay, that's the smallest x value we can throw in and still have a positive term inside our logarithm. Okay, so we're going to look for, or we have to have x being greater than negative 1. So we go back down to our solution. We have x is negative 5. This guy is impossible. Okay, one of those extraneous solutions that we talked about yesterday. So our answer for this one is 0.1926, or you could leave that as negative 5 plus root 29 over 2. Okay, so we're looking at solving our second example. We have log x plus 5 base 3, and we're looking at when that equals 5. Or sorry, when that equals 2. Okay. So how could we use this, or how can we solve that equation? Using our logarithms. What's the difference between our left side and right side right now? There's no log on our right side. But let's put a log on our right side. Let's multiply by 1, because we know that log of b base b is 1, and we're allowed to multiply by 1. So if we look on our left-hand side, we have log base 3. So let's put a log base 3 on our right-hand side, and let's multiply by log 3 base 3. Okay, we can multiply things by 1. That hasn't changed anything. But now that's going to look better for us because now we have two things that are both log base 3. Okay. So what could we do? What would be our next step? Still looking on our right-hand side. We can do something on our right-hand side. Let's bring that exponent, or sorry, the coefficient back up to as an exponent. So we're going to use that kind of rule in reverse, and we're able to write our right-hand side as log 3 squared base 3, and our left side is log x plus 5 base 3. So using that similar argument that we used on our example number 1, we have two things that are equal to each other that are log base 3. So we can say that whatever's inside our first, on our left side, x plus 5, that's going to equal 3 squared. We can evaluate 3 squared as being 9. X plus 5 equals 9. And then we can get a value of, or that x equals 4. Okay, we pull that back up, look at our original equation. X plus 4 is a valid solution. That's not going to cause us any problems. So our answer for this is x equals 4. Okay, so our third example, we're going to look at solving the log. We're going to have a base 3. Inside our log, we'll have the cubed root of x plus 2. And we're going to look at when that equals 1. Okay, so we have a logarithm with a cubed root in it, and we want to find out when that equals 1. So looking at that question, what's our kind of our biggest concern right now? What's kind of bothering us the most? The root. Kind of that cubed root isn't very nice looking. What is another way to write a cubed root with as an exponent? 1 over 3. So we can have log base 3 x plus 2 to the power 1/3. And we're still looking at that when it equals 1. Well, that's just an exponent. 1/3 is just an exponent. So we can pull that down out front. And now we can have 1/3 times log x plus 2. And we're looking at that when it equals 1. Okay. Yeah, sorry, it still is base 3. So all we did was just pull the exponent out front. Okay. What could we do at this step? What's still giving us trouble? So we have a right side, we don't have a log on our right side. On our left side, we still have a fraction here. So you could do a couple steps at the same time if you'd want. What we could do is if we multiply both sides by 3, and we can do that, as long as we multiply both sides by the same number, we're not changing anything. Our left-hand side, they're going to cancel out. And now we don't even need to write a coefficient of 1. We have the log base 3 of x plus 2. We want to find out when that equals 3. Okay. So now we can look at that and say, all right, well, let's put a log on our right-hand side. Let's put a log 3 base 3. We know that equals 1, so we're not changing our equation at all. Now we have a log base 3 on both sides. We can pull that exponent up, and we have log 3 cubed base 3 equals log x plus 2 base 3. So what can we do now? Okay, make what's inside our logs equal. So we'll have x plus 2 equals 3 cubed. 3 cubed is 27. So we're going to be doing x plus 2 equals 27. X equals 25.